For problem 6, I'm going to try a new layout, just because I don't have enough room to write on the page where I've given you the problem. This is a problem where we see a double pulley system again. So if I draw a force diagram for the load, and this is important, so if I consider this thing here to be my big block, where mg is 1250 newtons, its force diagram has its weight going downward, but tension from two different ropes going upward, right? Because whatever the tension in this rope is, it acts upward twice on the load. That's going to be important later. So now that we have the setup done, let me, on my facing page, think through all the parts. So what this problem is about, let me talk about that first. There's a broad concept that shows up everywhere in mechanical engineering called mechanical advantage. It's the, like for thousands of years before humans had sources of extra energy like steam engines, and even now that we do, um, much of our engineering has been centered around how we can make better use of the energy that our bodies or the bodies of our livestock are able to provide. So machines like levers, hydraulic lifts, um, inclined planes, crowbars, block and tackle systems like this one, all of them are designed so that we can exert a small force over a long distance on the thing that we touch, and then on the other side get a large force over a smaller distance. So let's see how this works. Again, many of our problems in this class are designed to guide you through understanding how a particular machine that you'll encounter in the real world works. So part A, how far must he pull the string? So imagine that he were to pull the string, say, 1 meter. Well, he's shortening the string by 1 meter. But since the string is wrapped around twice, wrapped around the load, taking half a meter out of each one of those would give him 1 meter of string. So let me write this out in text form here. Oops. So he must pull the string 2 meters for every meter the load moves. So you've seen this idea before. If I go back to my drawing, and I imagine like pulling little lengths of string here. So if he pulls the string, say, that much, then I have the same amount of string that's removed from the other side. So if he steps back, say that's 1 meter. If he steps back 1 meter, then that's going to go up by half a meter. That's going to go up by half a meter to keep the entire length of the string the same. So we can write that in symbols. Whoops, I'm on my wrong tool. 1 second, let me fix that. So the displacement of the person is twice the change in height of the load. So if he's trying to lift this 2 meters, then person, I can spell, then he must move 4 meters. Part B asks, what force must he exert? Going back to the force diagram that I drew on the other page, note that the acceleration in the y direction is 0, so so 2t minus mg equals 0, and thus t is a half of mg. This makes sense. The rope on the left supports half of the weight. The rope on the right supports half of the weight. But he's only touching the string once. So the force he must apply is equal to the tension. Which is equal to 1/2 mg. So mg here is 1250 newtons. So that is 625 newtons. So this is the essence of mechanical advantage. He only has to pull with 625 newtons to lift something that weighs twice as much. Part C, though, we think about work and energy. So the work done, so we're just going to calculate the work twice. So the work done by the rope on the load, let's see, that's going to be force times displacement, which is going to be here the change in height, is going to be 2t. It moved 2 meters. Whoops. So that's going to be 1250 newtons times 2 meters, which is equal to 2,500 joules. The work done by the person on the rope, here this is again force times the displacement, but here it's going to be the tension times 4 meters. You can already see this is going to come out to be the same. 625 newtons times 4 meters, which is also 2,500 joules. So in both cases, even though he's exerting a smaller force, he's got to pull twice as far and thus does the same amount of work. So this question presumes, the statement in the problem here, right, is that is he getting something for nothing? Oops. And the answer is he is in terms of force, but he's not in terms of energy, and energy is what is conserved. Part D and Part E are conceptual questions involving work and energy. So Part D says um, the rope is doing positive work on the load, so something else has got to be doing negative work on the load if its kinetic energy is staying the same. Well, remember, forces in the same direction as motion do positive work. Forces in the opposite direction of motion do negative work. So I'm moving upward. What force is pulling downward? Obviously, that is gravity. And for part E, why does this do negative work? Work is the dot product of force and displacement. There's no integral to do here because both force and displacement are constant throughout the motion. So here, the force is down, the displacement is up, and regardless of my coordinate system, down times up is negative. So this is a problem about, again, looking into the physics of mechanical advantage in a rope and pulley system. And now we're equipped to analyze it in two different ways. Once with dynamics, which we did in part B, well, parts A and B. This is the stuff you did before. But then in part C, we looked at an energy consideration, and we saw that even though mechanical advantage allows you to exert a larger force, have a machine exert a larger force than you do, it doesn't allow you to get energy from nothing. You still get the same amount of work out of the other end of the machine as you put in. This really makes ancient engineering remarkable, right? If you think about the engineering done by the Egyptians to build the pyramids, or the engineering by the Romans to build the aqueducts, or the engineering done by the Chinese to build the Great Wall, and all of those things, these people were very clever engineers and had access to machines that made good use of mechanical advantage to allow them to lift very heavy objects and exert very large forces when they needed to. But ultimately, at the end of the day, they had access to no more energy than they could provide with their muscles and the muscles of draft animals. And this is why kind of the big revolution, and the second big revolution in engineering happened when we started to have access to machines that would give us sources of energy that were not just muscle. Water mills, windmills, of course, were the earliest ones, but steam engines were really what let the Industrial Revolution take off, because they gave us an energy source to go along with all of our otherwise clever machines.